Everybody, welcome back. This lecture is going to be about the concept of net ionic equations, or what really happens when you put solids in water, like ionic solids. And last time we talked about the process of dissociation. Basically, you put an ionic solid in water. This happens to be a chunk of sodium chloride. And on dry land, so to speak, the sodium and chlorine ions have a very strong affinity for each other. They're very strongly attracted to each other. It's so strong of an attraction. This bond that's in here is so strong that even if you took this and slammed this with your foot, you couldn't break this bond. But the moment you put an ionic solid into water, the water molecules, and I like this picture because each of the water molecules shows the negative side here and the positive side for the hydrogens. The ions experience a huge attraction to the water molecules. They end up experiencing a greater attraction to the water molecules than these ions do to themselves. And what happens is the water molecules eventually pull them away. So we have negative ions that are being surrounded by the positive sides of water molecules. And over here, the positive ions are surrounded by negative ions. And I like this picture because if you look around the picture, you get to see these groupings of water molecules. That was my just got a text message. You see groupings of water molecules, but not all of the water molecules are being used. There's a water molecule up here. It's kind of hanging out over there. It's over here. That's kind of hanging out. And so someone looking at this solution right now would probably say this solution is unsaturated. So saturated, did I spell that right? Saturated. Saturated is a word we used last time to describe a solution that had so many ions dissolved in it that it couldn't literally handle any more water. Or sorry, it couldn't handle any more ions at all. It was completely filled up. But this solution has quite a few water molecules which are just kind of hanging around. So I would probably say that this solution is unsaturated. It could probably dissolve more ions before it becomes saturated. Okay, good. So one way that scientists try to look at what's actually happening when you put an ionic substance into water is to write something called an ionic equation. And I'm going to write an ionic equation right now. It's the same as a chemical equation, except it's got ions in it. So what I do is I start off over here. What's this stuff? This stuff is NaCl. And what phase is it right now? Any guesses what phase this matter is? Wait for it, wait for it, wait for it. Yes, it's got to be a solid. So this is sodium chloride as a solid. And it is going to dissociate. And I can write this like it was a chemical reaction, but we all know it's not. It's not actually reacting with the water. Um, there's no chemical reaction happening here at all. It's simply the ions are dissociating and as they become dissolved. So this sodium ion right here, I'm going to represent this here as Na, but not just regular Na. I can't just leave it Na. I have to leave it as Na plus 1. It's now an ion, but it's also no longer a solid. It is now dissociated and dissolved in water, so I have to write it as AQ, right? And there's another ion over here. There's chlorine. So let me get rid of my unsaturated word real quick. So in addition to sodium, I have chlorine ions. So chlorines are not just Cl's and they're done. They're Cl minus 1 ions and they're also aqueous. So this is what's known as you would call a net ionic equation. Net ionic equation, right? So this is what's really happening when you put salts into water. It's actually splitting into sodium and chlorine ions. Now you notice I don't actually write water over here. Water is not a product of this chemical reaction. First of all, there is no chemical reaction happening. Water just happens to be the medium that allows these ions to dissolve. So I'm never going to include the water as a product here. Let's just assume that the water is there. So what we're interested in is now we've got, this is just, it's kind of boring at this point just to put a salt like sodium chloride into water. What's really interesting is if I put two different salts in water at the same time. What if I was to mix two different salts? What would actually happen? I might get a chemical reaction to occur. So let's look at a common chemical reaction that might occur if you put two different salts together into water. So let's take a look at a hypothetical reaction. Let's take, I say, a salt like lead, Pb, what's a good solvent? How about lead nitrate? Lead's a +2 charge, and nitrate is a -1. So to make this work, I need 1 Pb and 2 nitrates, so PbNO3. And let's say I dissolve it in water, right? So I take this stuff and I dissolve it in water so I know it's aqueous. And let's say I want to react with it something like another soluble salt, like potassium iodide, Ki. So let's say I have two separate containers, one that contains lead nitrate and one that contains potassium iodide, and then I mix them. Well, what would I get? This is a nice double replacement reaction. Let's do a little bit of product prediction, right? I would get, my brother was texting me, that's why it's beeping. Potassium is going to want to grab the nitrate, and the lead is going to want to grab the iodide. And I would end up making KNO3, because potassium's a +1 and nitrate's a -1, plus Pb, lead's a +2, iodine's a -1, PbI2. Well, it's a simple chemical reaction, but here's the thing. Do I get to put aqueous down here on the potassium nitrate and the lead iodide? And the answer is yes for one of them and no for one of the others. Because when I write this chemical equation out right now, imagine I do this. Let me take a step back and let me erase the aqueous signs. And let me just write this whole thing as a simple chemical equation. Now, if you're looking at this chemical equation, you may just naturally assume that this chemical equation occurs. These two things chemically react together to make potassium nitrate and lead iodide. And I didn't balance this. Let's balance this. So we need a 2 over here with this, and then I need a 2 over here with this. And now it's balanced. So you might look at this chemical equation right now and assume that it's actually happening. But we know something a little bit different. We know that if I take this substance and dissolve it in water, it's not lead nitrate anymore. What is it? What is lead nitrate in water? Well, it's going to split into two different things. It is going to split into lead +2 ions that are aqueous if I put it in water, and it's going to split into two nitrate ions. So I'll put 2 NO3. I'm getting lots of text messages now. 2 nitrates, right? NO3 parentheses 2 means there's 2 nitrates, and they're both aqueous. So the moment I put lead nitrate in water, it's not lead nitrate anymore. It's lead and there's 2 nitrate ions. And the same thing with potassium iodide. If I put potassium iodide in the water, it splits into 2 potassium +1 ions that are aqueous, and it splits into 2 iodine ions that are -1 that are aqueous. So these two salts, and in chemistry, anything that's an ionic compound is basically a salt. They're not the same thing when you put them in water. So what's really happening is the moment I take all of these ions and dump them into a container which contains all of these ions, I might not actually be forming these two compounds, because in reality, I'm just going to have a grouping of 1, 2, 3, 4, 5, 6, 7 ions all coming together in a big ion soup. So imagine this. I'm going to take all of these ions here and all of these ions here and mix them together in one big container. So here's my beaker. And right now, what I have is, whoops, that's a lousy looking beaker. Let me erase that. So imagine I had a beaker full of lead nitrate and a beaker full of potassium iodide, and I simply take both of them and I dump them together. What am I going to get? I'm going to get a lead +2. I'm going to get 2 nitrates. So let's put a nitrate over here, NO3, NO3, and I'm not going to, I'll put -1 up top. And then I'm going to get 2 potassiums, K plus, K plus, and I'm going to get two iodines, iodine minus and iodine minus. So it's almost like, in reality, a chemical reaction that's performed in solution is something completely different. I have a whole bunch of ions which are all of a sudden present next to each other. Well, am I really going to produce potassium nitrate? Maybe, maybe not. It depends on this, right? And here's the big ticket item. It depends on whether the compound is soluble or not. So we're looking for this. I'm going to write this down. Okay, so this is a big one. Will an ionic compound actually form? Will a, let's put a red pen here, will a potassium come together and link up to form potassium nitrate, which is shown in this chemical equation? Well, the answer depends on whether potassium nitrate as a compound is soluble or not. And if the answer is this, if KNO3 is soluble, and just a quick show of hands, what does the word soluble mean? Soluble means this compound dissolves in water, because some do not. If potassium nitrate is soluble, then the answer is a big no. I will not actually form this compound, right? And it turns out that potassium nitrate is highly soluble in water, so I'm not actually going to form any potassium nitrate. But what about the lead iodide? It turns out that lead iodide is highly insoluble. Lead iodide, when it forms, insoluble. It's highly insoluble. So that compound will not dissolve in water. So what will happen is the lead will come over here and grab onto the two ions and actually form the compound, and then form something we call a precipitate, and it will settle out onto the bottom of the container. Okay, so this is a lot to handle. So in order to write a net ionic equation for a reaction that has an insoluble component, we have to look a little bit deeper, right? We have to look at and evaluate the solubility of different ions. So I'm going to show you a solubility table and then come back to this sheet. Okay, so it's like 8:24 in the morning and the teachers are all online and they're all posting on Google Hangouts. Okay, so what we're looking at now is a set of solubility rules. And this is something that's basically had to have been experimentally determined over like the past whatever 100 years. I don't know who actually ended up determining the solubility rules, but basically people had to sit there with every single compound that's known and try to see if it dissolves in water. So how does this work? Any salt that contains sodium, potassium, ammonium are automatically going to be soluble no matter what they've got. All nitrates, acetates, chlorates, perchlorates are soluble. Chlorides, bromides, iodides are soluble, except those that are containing lead, silver, mercury. And there's our winner right now. Lead plus 2. So we know that our compound that contains PbI2, whoops, there it is, I. Wait, where's our, yeah, chloride, bromide, iodide. Yes, sorry. That's our compound, and we know it is not going to be soluble. And the other compound we have, potassium, is here, and nitrate here. So from the solubility chart, we know that KNO3 is going to be soluble. So it's going to be able to be dissolved in water. But lead iodide is not. So what's going to happen is this. You mix these two chemicals together, all of a sudden, you're going to see this white powder appear inside your beaker. And it's going to be lead iodide. And lead iodide, because it's not soluble, is going to be a solid at room temperature. Oh, wait, I don't know why I just said room temperature, but it's going to be a solid when you mix these two things together. So there's a bunch of compounds that are soluble, and there's a bunch of things that are just not soluble. A lot of hydroxides, sulfides, carbonates are not soluble. There are some exceptions that are going on here. But this is a set of solubility rules which you are going to have to start to use. Now, I don't expect you to memorize this. Just keep it with you, all right? And I'm going to see if I can post a copy of this in along with the homework for this section. Okay. So I'm going to show you a reaction right now that has a precipitation going on in it. I'm going to show you a picture, right? So this is the picture of the process. You have two completely clear beakers. So this beaker here contains lead nitrate. This beaker here contains potassium iodide. Or rather, I think I have it flipped. So inside this beaker here is going to be a whole bunch of potassium and iodine ions that are completely separated from each other. Imagine each of these ions is going to be surrounded by a whole bunch of water molecules right now. In the beaker down below, we've got lead and nitrate ions. So for every lead, there's 2 nitrates that are floating around. The moment you mix, these two, you get this yellow precipitate. Well, what is yellow precipitate? It's this stuff. You get lead and iodide. So the lead, again, is the little gray right here. That's the lead. The iodide is the big purple. So you get lead and iodide ions instantly combining together to form this yellow precipitate. And eventually, all of this precipitate settles to the bottom of the container. So lead iodide is not soluble in water. So we know this. So it's not soluble or it's insoluble. And we know this from the solubility chart. So what does it do? The moment it forms, the moment this compound forms, it instantly forms something we call a precipitate. Precipitate. And that should be a familiar word because when it rains outside, we say it is precipitation. It is water that is condensing from a water vapor back into a liquid that is falling to the ground. And this will settle to the bottom of the solution, and it's like yellow snow is the best way I can try to compare this to. So we see a lot of things happening. We see um, two solutions come together. And these solutions, again, this is not lead nitrate that's inside here. It's lead ions and nitrate ions. This is not potassium iodide. It's potassium and iodine ions. But when it comes together, it definitely forms a solid out of the lead iodide. But what's left over? What's left over sitting up here? Potassium and nitrates. Potassium and nitrate. So the only thing that actually forms in this equation is this stuff. Lead nitrate is aqueous initially, so it's a whole bunch of ions. Potassium iodide is aqueous initially, it's a whole bunch of ions. And so is the potassium nitrate after the reaction. It doesn't actually form, it's only ions. There is no potassium nitrate in here. Now, if all of the water were to evaporate away, then you would see the potassium and the nitrate ions coming together to form a compound, but it's not. So what we have here is a situation where a whole bunch of ions have been mixed together. A whole bunch of ions have been mixed together, and we only end up forming one substance, lead iodide, as a result of the the lead and the iodide ions coming together. So it's a pretty amazing thing. So we were able to look at solubility. And solubility told us that potassium nitrate was soluble, but lead iodide was not soluble. And then we actually look at the process. So the next step is to take all this information and end up writing a net ionic equation as a result. Sound good? Let's pause for a minute. So we want to write a net ionic, a net ionic equation for the entire reaction. Now, here comes the terminology, and chemists love their terminology. This chemical equation that we wrote, we know if we put these things in solution, actually doesn't happen because I never actually have lead nitrate, I never have lead potassium iodide, and I never have potassium nitrate. The only thing that actually forms is this. So what chemists often call this is something called a molecular equation. And their reasoning for this is that they're imagining that you actually have this entire substance whole reacting with this substance. So they end up calling this a molecular equation. Now, you still could do this reaction if you mix lead nitrate powder with potassium iodide powder. You still could get a reaction to occur, but it's much, much slower. So anything that's taking place in solution, this equation we know is almost like it's a fiction. We know we're really not taking these two substances together. So the first step to getting a net ionic equation is to write something called the total ionic equation, right? Total ionic equation, which is often just abbreviated just the ionic equation, which is basically to separate all these things into ions. So right now, you can use this as a test, but we know that this, and this are all aqueous, which means they have to be split into ions, right? You could use the solubility chart as a test. So let's write all of these things as ions. So the lead is going to come down. Let's change color to blue. The lead is going to form Pb plus 2. And we know lead nitrate soluble, so it's going to be Pb plus 2 aqueous plus 2 NO3 negative 1 aqueous. And that finishes off the lead nitrate. Now I go to the potassium iodide, which is going to split into 2 potassiums and 2 iodines, plus 2K plus 1 aqueous, plus 2I minus 1 aqueous. Now I'm going to run out of room here, so I'm going to put the arrow here and put the rest of the equation down in the bottom. What else do I form? PbCl2. I know PbCl2 is insoluble, so I can't write PbCl2 as I don't know where I got Cl2 here. This should be PbI2. I'm really sorry if I wrote that up there. So PbI2, and it is a solid, so I can't split it into ions, plus 2 potassiums, 2K plus 1, which I know is aqueous, plus 2 nitrate minus 1, which I know is also aqueous. So this whole expression here is what's known as a total ionic equation. Now, here's something new. In a lot of cases, I ask people when I teach a subject, I ask them, what's actually happening in this reaction? And what's actually happening is lead is combining with iodine to form lead iodide as a solid. That's the only thing that's happening in this reaction. If you look on the slide before, the yellow stuff that's forming here is the lead iodide. That's literally the only thing that's actually happening. Okay, so what about nitrate? If you look at this, I start this chemical reaction with nitrate. And does the nitrate get chemically reacted? And if the answer was yes, then I shouldn't see any nitrate left over at the end of the reaction, but I do. This is nitrate appearing at the product side, which tells us that really nothing happened to it. Nothing happened. So can I write happened? So nothing happened to the nitrate. And if nothing happened to the nitrate, it tells us that the nitrate did not react. If the nitrate didn't react, then why bother putting it into the chemical equation? Can we find anything else that was there before and after the reaction? On the left side of the arrow and the right side of the arrow. It's right here. It's potassium. I have potassium before and I have potassium afterwards. So neither the potassium nor the nitrate reacted. They were there at the beginning. They're both here at the beginning and they're both here at the end. So things that are found before and after the reaction that didn't react have a special name. They are called spectator ions. And this is a really important term. If you plan on taking AP Chemistry, we talk about spectator ions a lot. So potassiums and the nitrates in this reaction are what's known as spectator ions because they basically do nothing. Spectators in a sporting event are sitting on the sidelines doing nothing, right? And they have to be. Look, they're both here at the beginning of the reaction, and they're both here at the end. So they didn't react at all. They're spectators. Okay, so in order to write my net ionic equation from the total, what we basically do is we leave anything that's a spectator ion, we kind of cross off. So let me get rid of spectator real quick. So anything that's a spectator ion, we leave out of the net ionic equation. So I'm going to leave out, let's change my color. Whoop, there you are. Let's make this green. Anything that's a spectator, I'm going to cross off. And the net ionic equation, I'm going to only write what's left. So what's left is Pb plus 2 aqueous plus 2 iodine minus 1 aqueous, going to form PbI2 as a solid. And that is my net ionic equation. Okay? So it's a process. We have to take the initial, what we assume to be a molecular equation, and determine are these things soluble or not. So I have to look at solubility rules to determine are these compounds soluble. If they are soluble, then I need to write a total ionic equation, which literally splits everything into ions. I then have to evaluate, do I have spectator ions? If I do, cross them off. And then I literally write what's left over as the net ionic equation. Okay, so let's do another example. All right, let me pick another problem and we'll go over that. Okay, everybody, we're back with another example. So we're going to go through the entire process and end up writing a net ionic equation. But the first step is to take our two initial reactants. All right, we haven't written the rest of the equation yet, but two initial reactants, and actually go and see, are these things soluble? Okay, ammonium carbonate. Take a look. So let's see. Let's find carbonates. Carbonates are not soluble, except those contain ammonium. Okay, so we're good. We know ammonium carbonate is going to be soluble in water, which means I can write this as an aqueous. All right, what about barium chloride? All right, let's go and check out barium chloride. So all chlorides are soluble except those Okay, good. So we know that barium chloride is soluble as well. So barium chloride is soluble. I don't know where our aqueous went over here. Now, let's predict some products. This is a double replacement reaction. I'm going to take barium, coming and grabbing a carbonate. Now, barium is a +2 and carbonate's a -2, so I'm just going to form BaCO3 plus, what's left? Ammonium and chlorine. Ammonium is a +1, chlorine is a -1, so I'm just going to form NH4Cl. And we should probably balance this. I need 2 ammoniums and 2 chlorines. I think I just got to put a 4. You know what, let me, not a 4, but a 2. Let me just rearrange this and rewrite it. Okay, now do the same thing. Take barium carbonate and ammonium chloride and go back to our sheet. Are they soluble in water or not? So where are we? All sodium, potassium, ammonium compounds are soluble. So the ammonium chloride is good. Let's look for barium carbonate. I don't see barium up here. Let's go down to carbonate. Carbonates are not soluble except for those containing sodium, potassium, ammonium. So I think we found our winner. So we know that the ammonium chloride is going to be soluble, so I can write in AQ, but the barium carbonate is going to be insoluble. That's going to be this is going to be our precipitate. I'm trying to write precipitate. There we go. Okay, so now let's write a net ionic equation. Let's change colors here and go to blue. So ammonium carbonate is going to split into 2 ammonium ions. So I'm going to write 2 NH4 +1 aqueous plus carbonate CO3 -2 aqueous plus barium chloride is soluble, so I end up with barium +2 aqueous plus how many chlorines? There's 2 Cl2, so there's 2 Cl -1 ions that are also aqueous. Now, I'm going to write the rest of the equation here. So what am I going to form? Barium carbonate is insoluble, so I know it's going to be a solid, so I can't split that into ions. BaCl2. Where did I get, where am I feel like I have chlorine on my brain right now. Hold on. It's not BaCl2, it's barium carbonate. BaCO3, solid, plus the other products. Ammonium chloride, so I'm going to form 2 ammoniums and 2 chlorines. 2 NH4 +1 aqueous plus 2 Cl -1 aqueous. Okay, so this is our total ionic equation. Now I need to see if do I have any spectators. And a spectator ion is something that's there before and after. So let's switch to red to eliminate spectators. So I think here's our first one. I have ammonium before the reaction, ammonium after. And then what's left is carbonate. Is carbonate a spectator right now? Do I have carbonate ions before and after the reaction? And the answer is no. Barium carbonate after the reaction are not ions. They form a solid precipitate. So carbonate's not a spectator. Barium's not a spectator. It's got to be chlorine. I have chlorine before the reaction to the left of the arrow and chlorine to the right of the arrow. So if I eliminate all of my spectators, whatever is left is going to end up forming my net ionic equation. So carbonate plus barium goes to form barium carbonate. All right. So let's write that in green. So CO3 minus 2 aqueous plus Ba plus 2 aqueous. And you can rewrite this if you want to. You don't have to write them like that, but I just keep them the way I find them. Is going to react to form BaCO3 as a solid. All right, and that's it. That's my net ionic equation. So why? The net ionic equation is really important. It's a useful tool, but like, does anyone ask the question why barium carbonate forms the precipitate? Why barium carbonate's not soluble? And in the preceding problem, where are we? In the preceding problem, we had lead iodide is insoluble. So let's take another look. We've got barium carbonate is insoluble, and we had lead iodide that's insoluble. So what is it about them that they don't like water? So if we come back to a regular solid, something like NaCl, we know NaCl or NH4Cl or KNO3, any of these things are soluble, which means that when they go into water, they are going to form ions. And why do they form ions in water? Someone writes, all right, ions in H2O. And the reason is, how do I write this down? Let me pause for a minute so I can write this down. All right, so I kind of summarized it like this. These substances are all soluble in water because the water forms a greater attraction. The water has a greater attraction to the ions than the positive and negative ions do to themselves. So all these positive and negative ions are all attracting to these things as solids. If I had all three of these substances on the table, they would all look like white salts. It's because the positive, negative, positive, negative, positive, negative ions are all attracted to each other. But the moment you put them into water, these ions have a much greater attraction to the water molecules than they do to themselves. But what about something like lead iodide and barium carbonate? Well, these substances are different. These substances tell us that when a lead plus 2 ion finds 2 iodine minus 1 ions in solution, it kind of violates this rule, right? So these ions violate this rule. Well, what's this rule again? This rule says the water is more strongly attracted to the ions. In this case, how do I figure out why lead iodide forms at all? It's because in this case, we have something different going on. In this case, these ions are more strongly attracted to each other. So this is a different scenario. The lead and the iodine ions have a much greater attraction to each other than they do to the water. And there are circumstances like this. Look at the solubility rule chart. There's lots of things on here which are simply not soluble. And the reason is this. They typically have large charges or very small sizes, right? And I'm not going to get into the whys or wheres on this right now, but suffice to say that there are some compounds out there where a barium is much more strongly attracted to the carbonate than the barium is attracted to H2O or the carbonate is attracted to the H2O. The lead is much more strongly attracted to the iodines than the lead is attracted to water or the iodine is attracted to water. So there's a whole series of compounds out there which we know is just insoluble in water. They just don't dissolve. But what it's really saying is there's a much greater attraction between these ions in themselves than these ions in the water. So that's kind of more of a theoretical reason why we have insoluble compounds. Can you think of any other insoluble compounds? Yeah, go pick this up. CaCO3, calcium carbonate, right? Where do you find calcium carbonate? So calcium carbonate is basically the chemical that makes up something called this. This is limestone. We have limestone. Limestone or calcium carbonate is the basic chemical that makes up all of the shells and seashells. This is coral. These are the little organisms that live in coral reefs. It's all made from calcium carbonate. Why? Why is can it be made from calcium carbonate? Because calcium carbonate is insoluble in water. I mean, it dissolves a little tiny bit, and if you take AP chemistry, we'll talk about how much, but it doesn't dissolve in water because the calcium plus 2 ion is very strongly attracted to the carbonate minus 2 ion. They don't want to break apart from each other. That's like all happy. So calcium and carbonate are more strongly attracted to each other than they are to water molecules, which is why I can have coral reefs or seashells or limestone or marble or whatever. And interestingly enough, is that if you keep putting more of this stuff in the atmosphere, more of it dissolves into water to make it acidic, which means this stuff dissolves. Under very acidic conditions, calcium carbonate will dissolve, which means these things become smaller. That's an S. These things become smaller. These things die. Um, Try it. Go take a piece of calcium carbonate and put some acid on it, and it'll start smoking and dissolving as it makes carbon dioxide. So we see these types of things in nature. We see insoluble compounds all over the place. Incidentally, you might even have things known as hard water deposits. Let me show you a picture of hard water deposits. So here's a hard water deposit. This is a sink, the end of a sink, and if you have stuff known as hard water, this is water that has a lot of minerals dissolved in it. You could have calcium ions, you could have magnesium ions, carbonate ions. As soon as these ions end up meeting and evaporating away, what you see growing here is it could be calcium carbonate, right? It could be a compound that is insoluble where the ions are more strongly attracted to each other than others. Okay, a lot of stuff going on today. We started talking about, we introduced the idea of net ionic equations, what's really happening in water with ionic compounds. And we found out that from last time, ionic substances that are soluble end up getting picked up and carried away by water molecules. We wrote a net ionic equation to describe what happens in water. We looked at solubility. Oh, I lost my solubility somewhere. It's up here. Where's my solubility chart? We found out that certain ions are soluble in water and certain ions are not, certain compounds rather, and this is all done by trial and error. No, you do not have to memorize this, but you can use it as a tool, and we figured out ultimately how to write a net ionic equation. Okay, so there's a reading in the book. You should download the book. It starts on page 346. It has example problems on it. There's also homework that I'm going to give you, and I'm going to post a couple videos, YouTube videos for describing how to write net ionic equations. I hope you have a great day. By the way, ask me questions.